online speaker. Yeah. So our online speaker, so this will be lecture about classical estimation theory, as I told, and it's my great pleasure to introduce you our colleague, Professor Andrey Pilipenko. Professor Andrey Pilipenko is is a leading researcher at the Institute of Mathematics of the National Academy of Sciences of Ukraine. He also a professor at the Kyiv Polytechnical University. Currently, he is working at the University of Geneva. Yeah, so this is why he's online now for you. And Andrey Pilipenko is an outstanding expert in stochastic problem, in classical stochastic tasks. So I could say you that this is maybe one of the most outstanding Ukrainian scientists in what about stochastic processes, stochastic science. When we have in Kyiv at least, or in Ukraine at all, some statistical problems, some stochastic problem, we usually go to Andrey Pilipenko. This is from people in industry, also people from in academy. And Andrey was also has a lot of courses in USA, Germany, Norway, China, Switzerland, and in 2023 he received a prize. So for the best paper published in the journal Stochastic Processes, ITO Prize. Yeah, well-known, well-established prize, and for the paper which solved a long-standing problem. So, Andrey Pilipenko will talk us about classical estimation theory. So, together with what I taught you before lunch, after lunch, this is the second component that you need to understand tomorrow lecture about quantum tomography. So, Andrey, can you hear me?
Yes.
Yes, you can share your
yes
because you can write, I know, yeah, notes.
Yes, thank you very much for introducing. It's a great pleasure for me to present a lecture today. So today we study a classical statistical equation about estimating of point estimators of parameters. So the general problem is the following. By the way, do you see my screen?
We can Zoom now. I don't know if it's your screen. No, not really.
One more. Okay,
not really.
try. And now? Do you see a whiteboard?
Yes, yes, yes.
Do you see whiteboard? Yeah.
Okay. So what do we usually have? We have some data, x1, x2, and so on, xn, that comes from certain experiment. And we want to, so this data is random, and we want to answer some questions. For example, we want to find expectation of x or variance of x, and so on and so forth. And what are the experiments? For example, you send a signal and xn may be 1 or 0 if you send a signal successfully or with a failure. Or for example, one person sends signal and the second person measure some properties of this signal. But you have random perturbations. And you would like to find, for example, expectation or some other properties. Yes. Yes. Pardon? Hello? And now, is it better?
Yes, everything's fine.
Okay. Or you observe some physical law and you want to find properties of the distribution of x. Well, when I say that we have a sample, we will always assume today that x1, x2, and xn are independent, identically distributed random variables. Identically distributed random variables or random vectors. Well, if you know the distribution, there is no problem to calculate expectation or variance. However, usually you don't know the distribution. And my aim is to explain you some methods of calculating parameters of distributions or so we cannot find expectation if we don't know the exact distribution. However, we can estimate, and our aim is the following. If n is large, then our estimate should be closer and closer and closer to the parameters. Well, sometimes we will know that, okay, expectation, variance, distribution function, or sometimes people say cumulative distribution function or density function, probability density function. Density function, p of x, and so on and so forth. Sometimes we will not know anything about the distribution, just that expectation is finite. But sometimes in certain experiments, we know more. And sometimes we know that the distribution has special form and depends on parameter. For
I'm really
example,
sorry. I'm really sorry to interrupt. I think
yes.
okay, there was just an internet connection in the university, but I think right now everything's fine. Uh, yes, sorry for
Yeah,
this.
Andrey, I'm sorry to interrupt you also. So we have short maybe the last 3 minutes only when your var x has written. This was because we had a problem with internet connection.
No problem.
Okay, can you please repeat?
Okay.
Yeah.
So
I'm sorry for this technical problem.
So I'm going to explain you methods of approximate so we want to calculate expectation, variance, distribution function, probability density function, and so on and so forth. And today I'll present certain methods how to do it. Sometimes we don't know the distribution of x, but sometimes we know that, for example, distribution of x is exponential or normal distribution or binomial or Poisson. And then we can say more. For example, sometimes it's known that distribution of x is exponential. What does it mean? This means that the density, probability density function has a certain form. Px theta is equal to theta e to the minus theta x if x is non-negative and 0 if x is negative. And the question is, find the parameter theta. And if you find this theta, then you can find expectation, variance, distribution function explicitly. And sometimes you know from the very beginning that results are exponential. For example, usually the waiting time of certain events have exponential distribution. Why? Because exponential distribution has so-called memoryless property. So if you observe some elementary particle and you wait the next one, then it's natural to expect that density, that the distribution is exponential. Or sometimes it's natural to expect that certain random variables have normal distribution. For example, usually people assume that errors of measurable of measurement have normal distribution. This means that probability density function. So now theta is two-dimensional parameter, a and sigma squared. A is real number, sigma squared is non-negative, is positive number. Then the density has the following form: 1 over square root of 2 pi sigma squared e to the power minus x minus a squared over 2 sigma squared. Or, for example, binomial distribution. binomial distribution with parameter n and p. It describes the following with parameters n capital and p. It describes the following problem. Assume that we have n experiments. Sorry, n experiments. And probability of success is p. Probability of success in each experiment. And assume that all experiments are independent, and x is just number of successes. It's well known that x has a discrete distribution, and the distribution is the following. Probability that x is j is equal to n choose j, probability of success times j, times probability of failure to the power, n capital N minus j, where j is integer number between 0 and n, and n choose j is n factorial over j factorial times n minus j factorial. So in this case, we are going to find p, probability of success. Okay, so sometimes we have discrete distribution, sometimes we have continuous distribution. Oh, by the way, if we have discrete distribution, then this distribution will be denoted the following: p, j, theta also. Now, theta is p is probability of success. So I will not distinguish probability density function or just probability. Well, and the next step, when we estimate a parameter theta, our aim is to construct natural approximation of theta. But what do we really can do? We can calculate some functions of this sample, maybe sum, average, sum of squares, product, maximum, minimum, and functions of a sample t of x1 and so on, xn, are called statistics or estimators. So function of a sample, function of a sample is called a statistics, a statistic, or an estimator. And if we want to estimate parameter theta, then we say, okay, this is an estimator of theta. Sometimes I will, if I estimate theta, then I will denote an estimator by theta with hat or theta with star. Sometimes I will add subindex n. Sometimes I say that, okay, let's consider estimator that depends on x1, xn, or just use some t or other function. But we want to find nice estimators, and we say that theta sub n is consistent, is a consistent estimator of the parameter theta if theta n, if this estimator converges to theta as n tends to infinity in probability. However, here I should stop and make one remark. If I write, say, I know that distribution is exponential with parameter theta. I don't know what is the parameter theta. I don't know. I know only that theta is a non-negative number, and the density has the following form. There is one true parameter, and we want to find it. And it's more accurate to say the following. We have certain distribution with certain density, for example, where theta belongs to a certain set. For example, here this set is 0 infinity. And we say that theta n hat is a consistent estimator of theta if for every theta from this set of all possible values, we have convergence in probability. And moreover, I have to mention that this probability depends on the parameter. Okay, now this definition is rigorous. And if we have convergence with probability 1, then we say that the estimator is strongly consistent. So if theta n hat converges to theta with probability 1, then we say that theta n hat is strongly consistent estimator. Maybe I have to recall the definition of convergence in probability and convergence with probability 1. This means that for every epsilon greater than 0, probability that this estimator and the distance between estimator and theta is larger than epsilon goes to 0 as n tends to infinity. Well, and probability depends on theta. So theta is the true parameter. And here, convergence with probability 1 means that probability that a limit of n tends to infinity theta n hat is theta is 1. It is well known that if you have convergence with probability 1, then you have convergence in probability. Okay, and now let us discuss methods. How to find consistent or strongly consistent estimators. And one of the most important results in this direction is the law of large numbers. Numbers. And let me recall you the following theorem. Assume that xk are independent, identically distributed random variables with finite expectation, and expectation of absolute value of x is finite. Well, I can write here x1, x2, x3, xk. They have the same distribution, so I will not write an index. Then the average of x's converges to expectation of x as n tends to infinity with probability 1. Sometimes this statement is called the strong law of large numbers, or Kolmogorov strong law of large numbers. And sometimes people say that average in time converges to average in space. So average of x, integral of x with respect to the distribution. And now let me consider a few examples of constructing of consistent or strongly consistent estimates. The first example is Poisson distribution with parameter lambda. And let me recall you that this is a discrete distribution such that probability that x is k is equal to, Poisson with parameter theta. Theta to the power k times e to the power minus theta over k factorial, where k is non-negative integer number. Well, it is well known that the expectation of x is equal to theta. So by the strong law of large numbers, x1 plus x2 plus xn over n converges to theta, to the expectation, theta, with probability 1. So corollary is this mean, so theta hat n, which is equal to the average, is strongly consistent estimator of theta. Okay, let's consider one more example with exponential distribution. And the density is this. And it's also well known that expectation of x is the following: 1 over theta. Now we don't think, we just say, okay, let's try the average and apply the law of large number. This converges to 1 over theta as n tends to infinity with probability 1. Hence, n over x1 plus xn converges to 1 over theta, so to theta with probability 1. So this is strongly consistent estimator. And if you use standard distribution like normal, binomial, exponential, geometric, Weibull distribution, then usually the expectations are known, and very often they coincide with the parameter. Well, now let's consider more tricky example. Assume that we observe a sample from the following discrete distribution. Assume that these random variables may have 3 values, plus or minus 1 with probability theta, and probability that x is 0 is 1 minus 2 theta, where theta is certain parameter between 0 and a half. well, theta plus this number is 1, and all these numbers are non-negative, so this is really probability distribution. So the first step is the following. Let's apply the law of large numbers. And let's calculate expectation of x. And expectation of x is some value times probability, so plus 1 times theta plus -1 times theta plus 0 times 1 minus 2 theta is 0, and we know that sum of x's converges to 0. And probably using this statistic was a bad idea. So let us apply law of large numbers again, but to different but not to random variables x1, x2, xn, but another one. For example, absolute value of x1, absolute value of x2, absolute value of xn. And well, x's were independent, so absolute values are independent again, and we know that this average converges to expectation of absolute value. And now let's calculate. So 1 times theta plus absolute value of -1 times theta plus plus absolute value of 0 times 1 minus 2 theta. So equals to theta. This statistic converges to theta with probability 1. So if we divide the left-hand side by 2 and the right-hand side by 2, then we see that the sequence of these random variables converge to theta as n tends to infinity with probability 1. So this statistic is consistent estimator. Okay, we see that the law of large numbers works, and it works good. We just we don't think we find the expectation of x or absolute value of x, and if we can find this parameter theta as a function of the expectation, then we are done. And the corresponding method is called the method of moments. Let me formulate it. So, method of moments.
Maybe at this point someone has questions. Just checking.
Yes, if someone has a question, do not hesitate to interrupt me and to ask.
Do we have a question in the audience? Here, locally? It seems that not, Anton.
Okay, yeah, I
Okay.
also don't have a question, just checking.
Okay, so let us continue. Let me recall that the case moment of a random variable x is expectation of x to the power k. So m1 is just expectation of a random variable. And now assume that x1, x2, and so on be a sample, so independent, identically distributed random variables. And we know that the average of x's converge to expectation of x or m1 the averages of squares converges to expectation of a square M2 and so on and so forth. The averages of, say, piece moment of random variables converges to x to the power p, which is piece moment. Well, now we assume that there is a certain parameter and distribution of x depends on a parameter theta, and assume that there exists a continuous function f. There exists a continuous function f such that f of m1, m2, and so on, mp is theta. Well, I have to make again remark. If the distribution depends on theta, then the first moment, honestly, it depends on theta. The second moment depends on theta. This moment depends on theta. Well, and okay, when we integrate, density depends on theta. So here I should write that f of m1 of theta, m2 of theta, mp of theta is theta, and I assume this for every parameter theta. Now I have a sample. I know this convergence. So if n is large, then this average approximately equal to m1. It converges to m1. And this converges to m2. And this converges to mp. And I assume that f is a continuous function. So then f of average of xi, average of squares, average of piece power converges with probability 1 to f of this converges to m1, m2, and so on, mp, which is equal to theta. Here I used continuity of f, and I also used the strong law of large numbers that this converges here, here, and there. Corollary. The corollary is the following. If you have this, then this statistic is consistent estimator. Estimator of theta. And one remark, you see, averages.
Andrey, may I ask a question?
Yes,
maybe this
sure.
is, yeah, maybe this is a little bit in audience. You don't have maybe a little bit in advance, but what about biasness of this method of?
We will discuss it a little bit later.
Okay. So
we will discuss is estimate good or bad, and we discuss certain
biasness,
quality of estimators. But this is a way to construct an estimator. So the first thing is to find nice estimates. And the second question will be, yes, I agree with you. It's very important. We have to decide which one is better. Which one is better? But later, you see, we use averages very often, and sometimes it's convenient to introduce notation, the following notation. The average of x is denoted by this like x bar. And sometimes statisticians say that this statistic is called the sample mean. The sample mean. And when you consider average of squares, then we just use the following notation: x squared with bar. And now let's apply this method. And let's estimate variance of a random variable. So we have a sample x1, xn, and we assume that the second moment is finite and sigma squared is variance of x, and we want to estimate sigma squared. So let me recall the formula for variance. It is expectation of square of deviation of x from the mean, or if you open parentheses and make some cancellation, we can see another formula: expectation of x squared minus expectation of x squared. So this means m2 minus m1 squared. So this is second moment and this is first moment squared. So corollary from the method of moments is the following. Let's take a function f of m1, m2 is m2 minus m1 squared. So second coordinate minus square of the first coordinate. We see that this function is continuous. And it follows from method of moment that average of squares minus sample mean raised to the second power is a strongly consistent estimator of the variance. Is consistent estimator of sigma squared. By the way, there are two formulas for variance. It is not difficult to show that this formula, this estimator is equal to the following: sum of xk minus sample mean squared over n. Actually, this formula is very natural. You see, the sample mean goes here. And now we apply the law of large numbers. We want to calculate the following sum. Sum xk minus expectation squared over n, and say, well, by the strong law of large numbers, this converges to sigma squared. But we don't know expectation of x, and we replace expectation of x with the sample mean and obtain this very natural formula. I will discuss bias a little bit later. I just let us continue and
Can I have a quick question?
yes, sure.
So we're basing our estimator, like we're calculating the sample, like as a sample mean, and then we're basing it on the law of large numbers. Is there any other way, or like the estimator is basically based on the law of large number?
Yes, there are few methods, but I would like to say that the law of large numbers in different forms is very applicable. And you see, for example, sometimes we use this formula with squares or with means. Sometimes we take absolute values as in this example, and there are another methods, and now we, for example, maximum likelihood estimator. But now let us apply the law of large numbers and method of moments one again, and you will see that it's applicable. It's applicable, and you don't think. You just calculate moments and then represent parameter sigma or theta as a function of means or moments.
Okay, thank you.
And okay. However, there is one important question. Okay, so problem. We know that the sample mean is a consistent estimator of the sample mean, and assume that we multiply this one by certain number, for example, n over n minus 1. Okay, sample mean converges here, this converges to 1. So this product converges to expectation, and hence this is also consistent estimator of expectation. But which one is better? So which estimator is better? You may say, well, the formula is simpler here, so probably this one is better, and in some sense, this is correct answer. However, you may also ask the following. Well, this sum of x case minus x bar squared over n converges to sigma squared, converges to variance. And again, let's multiply this by n over n minus 1 and consider the following. Estimate over n minus 1. It also converges to sigma squared, and natural, okay, not natural, but there is a question, which one is better? And if you open Wikipedia, for example, and if you ask the following question, how to estimate variance, then you will see n minus 1 in denominator. And there is a question, why? Why do people write n minus 1, not n? Maybe by mistake, or there is some deep reason. And our next topic is called biased and unbiased estimators.
Andrey, sorry, maybe some questions because between topics. Okay, can you hear me?
Yes.
Yes.
Yeah. Yes, students, do you have questions here? Offline, don't have. So,
Yeah.
Anton, do we have something
in chat? We don't, but yeah, don't be shy to write something or raise your hand. You can just do it during the lecture, and then I'll read it, and I'll read all the question in between the breaks.
Okay, then go ahead.
Okay, let's continue. And I start just from the definition. The estimator theta is called unbiased estimator of theta if for every theta expectation of theta n is equal to theta. Well, we know that we know the definition of consistent, and consistency is very natural. However, sometimes it's very natural to ask maybe in average of your estimator is theta. So roughly speaking, 50% your estimate is above, 50% is below, and there is no bias. And sometimes people want to construct not only consistent or strongly consistent estimators, but unbiased estimators too. We will discuss a little bit later other nice property of estimators. But now unbiased estimator is nice property. And well, there were two questions, which one is better? And let me answer. So at first, let me find the expectation of the sample mean. So the sample mean is a random variable. It has a certain distribution, and let's calculate expectation of the sample mean. So expectation of x1 plus x2 plus xn over n. So n is constant. We know that the property of linearity for expectations, and expectation of sum is equal to sum of expectations. And all of them are equal. x1, x2, xn all of them have the same distribution. So n times expectation of x1 or x2, n is cancelled, and corollary is the following. The sample mean is unbiased, well, and strongly consistent estimator of the expectation, so corollary. Sample mean is unbiased and strongly continuous, or strongly consistent estimator of the expectation. And one more example. Consider Poisson distribution. Let me recall you that the expectation of x is just theta, is just parameter. So hence, sample mean for Poisson distribution is unbiased and strongly consistent estimator of this parameter. Or one more example. For example, okay, this example. Is this estimate unbiased or not? Let's calculate its expectation. So expectation of plus x n over 2n. However, we don't have to think about this. So it's if you divide by n, we know that the answer is expectation of absolute value of x over 2. And we calculated expectation of x. So the answer is 2 theta over 2 is theta. If we consider this example, then it is a question how to calculate this distribution. It is not true that expectation of without absolute value, excuse me. It is not true that expectation of 1 over random variable is equal to 1 over the expectation. So this is incorrect. If you want to check if this estimate unbiased or biased, you have to calculate at first the distribution of the sample mean and then integrate and obtain the answer. So actually this is a nice exercise. And now let us continue and let us discuss these two estimates. Are they biased or unbiased? Well, so let's calculate at first the expectation of the first statistics xk minus x bar squared over n. Well, it's easier to write the following formula. Minus expectation of the sample mean squared. And well, again, we apply linearity term 1 plus term 2. And the first part is just equal sum of expectations of xk squared over n is equal to expectation n times expectation of a square. So the answer is this. Just second moment. If you wish to calculate the expectation of the sample mean squared, then you have to open parentheses and make some transformations. So at first, let me write 1 over n squared before the expectation. So n squared, and now open parentheses, and we have sum of squares. Plus sum of products. So let me write like 2 sum of products x, k, x, j, where k is less than j. We apply linearity and result is this n times expectation of a square plus 2 expectation of a sum is equal to sum of expectations. And k is not j, so xk and xj are independent. So expectation of product is equal to product of expectations. So let me just write expectation of x squared. All of these expectations are equal, and the number of pairs k less than j is equal to n choose 2. So we have to select two distinct numbers of n. This n choose 2 equals n factorial over 2 factorial n minus 2 factorial. So 1 times 2 times 3 times n minus 2 n minus 1 n. 2 factorial is just 2, and n minus 2 factorial 1, 2, 3 times n minus 2. This and this cancelled, and the answer is n times n minus 1 over 2. And we continue our calculations. So the answer is n divided by n squared expectation of x squared. So expectation of x squared over n plus 2 times this number, so plus n minus 1 times expectation of x raised to the second power, and divided by n squared, and we cancel 1n. And now let me write the final answer. So expectation of sum of xk minus x bar squared over n is equal to n times expectation of x squared. So this first term, and minus I2 minus this number minus excuse me, this n is incorrect, just expectation square minus expectation of x squared over n, and minus n minus 1 over n square of the expectation. So we cancel here. So expectation of x squared and 1 minus 1 over n is n minus 1 over n. So n minus 1 over n. So the answer is n minus 1 over n. Second moment minus square of the first moment. So the answer is n minus 1 over n times sigma squared. So corollary, this estimate is biased. And if you calculate expectation of the following ratio with n minus 1 in denominator, and if you use linearity of the expectation, then you will see that the answer will be this, but divided by n, multiplied by n, and divided by n minus 1. Hence, this estimate this was biased, and this estimate is unbiased estimator of the variance. And these statistics is called sometimes unbiased sample variance. So this statistic is called unbiased sample variance. Sometimes people say just sample variance, but some probabilists and statisticians call this statistic sample variance. So statisticians, unfortunately, do not agree on notations or definitions. So sometimes, it's convenient to add this word, unbiased sample variance, and you understand that you have n-1 in the denominator, and now we understand that this estimator is a little bit better than this one.
Okay, Andrey, it seems that it's time to make a coffee break.
Yes.
Maybe questions before.
Yeah. So let's make a short, like 5 minutes coffee break, and
do we have some questions? Do we have some questions? Here, yep. Just a moment. We have questions from audience. Yeah.
Yeah. So just to make sure, do I understand correctly that to check if the estimator is unbiased, we need to look at this function f of momenta as we have done earlier, and just took the expectation value of this and checks that it converges to the same value of parameter set theta.
Do you mean this one?
Yeah.
Theoretically, yes, but sometimes it is very difficult to calculate expectation of f of this, because you see, when we have sample mean or sample variance, it was very easy to calculate. It was very easy to calculate the expectation. But if you try to calculate, say, sine of x1 plus xn over n, where, for example, xk have exponential distribution or binomial distribution or certain distribution, then sine of expectation of sine is not like sine of expectation. So it may be very difficult, or moreover, it can be impossible to calculate the expectation, to obtain nice formula. If the function f is simple, like some linear combination, then it's possible to check is the estimator biased or unbiased. However, for complicated formulas, it may be difficult. On the other hand, usually all formulas are quite simple, like sample mean, sample variance, and so on and so forth. It's not usual to have very tricky formula like sine of arctangents of square root of 1 plus product of random variables. No. So usually in applications you have normal functions, good functions, and you will be able to calculate. However, sometimes it's impossible to find unbiased estimator. Well, assume that you get the following. Okay, we will discuss this after the break.
Okay, thank you.
More questions? Maybe some questions from online, Anton?
No questions from online.
No question. So, okay, then coffee break, but I would like to say now 10 minutes coffee break. And during coffee break, we have so-called free microphone. If you want to discuss this lecture something, you can take your coffee, give lecture chance also. Continue, okay.
Now I would like to discuss one example that shows that if you use methods of moments, sometimes it's very difficult to calculate unbiased estimate. And example is the following. Let x1, x2, xn be a sample from exponential distribution with parameter theta. And but we assume that we do not observe x, but we observe the following random variables yk, which are equal to minimum of xk and 1. So we observe yk k between 1 and n. You may ask me why it's natural to observe these random variables. And the answer is the following. Such procedure appears very often when you cut the time of observation. For example, you test certain pills or drug or some medical treatment, and you have a sample of people, and xk is a waiting time before case person become healthy. But you study not all the life of a person. You just study 1 day or 1 week or 1 year, and then you stop the observation. So if a person become healthy before 1 year or 1 week, then you say, okay, he become healthy at the moment by K. Otherwise, you just stop observation and you know that a person was ill until the 1 year. Or, for example, you can wait certain signals, and you can wait, say, 1 millisecond or 1 second, and then you stop observation. And if signal arrives before, you get it. If no, then not. Well, and now let's try apply method of moments and calculate expectation of yk. Let me recall you that density of x is theta e to the minus theta x if x is positive. Oops. Theta e to the minus theta x if x is positive, and we want to calculate the expectation of minimum of x and 1. So the integral from 0 to infinity value minimum of x and 1 times density theta e to the minus theta x dx. Okay, I did some calculations at home, and if I am correct, okay, maybe I made a mistake, just double check me. Then the answer is the following: 1 over theta 1 minus e to the power minus theta. So if we use method of moments, then we know that the expectation of these, the average of y's convert to this number. And if you wish to apply the method of moments, you have to find a function f such that f of 1 minus e to the minus theta over theta is theta. So I don't know. Is it possible to write analytic function f such that you have the following equality for every theta non-negative number? Well, you may say, okay, let's calculate expectation of y squared. Maybe it is a good idea, I don't know. Just try and maybe you get some nice formulas, but I'm not sure. However, the question to construct, yes, and you see, here it's difficult to calculate consistent estimator and unbiased. So I don't know how to correct this, even if I find the function f or write certain representation, for example, Taylor series, then it would be very difficult to correct the corresponding estimate and to make it unbiased. So two questions. Consistency and bias and unbiased may be complicated. However, the question is natural. How to calculate at least one consistent estimator of parameter theta. And well, we can use different functions. Here we use just y. We can use y squared, y cubed, y to the power p. I'm not sure that you will see nice formulas. And let us use the following function. Consider random variable zeta k that is equal 1 if yk is 1 and 0 otherwise. If yk is less than 1, okay, is not equal to 1. We know that yk is equal to 1 if and only if xk is greater than 1. So 1 if xk greater than or equal to 1 and 0 otherwise if xk is less than 1. And sometimes we write indicator function such 1 and we write xk greater than or equal to 1. So I call this function indicator. So 1 if this condition is satisfied and 0 otherwise. Well, if xk were independent identically distributed, then zk are also independent identically distributed, and we know that the mean of zetas converges to expectation of zeta with probability 1. Now let's calculate expectation of z. Z is discrete random variable, and it takes two values, 0 and 1. So expectation of z is equal to 1 times probability that z is 1 plus 0 times probability that z is 0. And this is just equal probability that z is 1. And please remember that expectation of indicator is equal to probability of the corresponding event. So this probability is equal to probability that x is greater than or equal to 1. So integral from 1 to infinity, density, theta e to the minus theta x dx. We integrate and obtain e to the power minus theta. Okay. This function is much better than this one. Really, if I can find the inverse function, and the inverse function is minus logarithm, and if theta converges here, then minus logarithm of the average of zetas converges with probability 1 to theta as n tends to infinity. And hence, corollary, this is consistent estimator. So just count number of x's that are equal to 1 and calculate the average, take logarithm, minus, and if n is large, then these statistics approximately equal to theta. However, it is a question, is it biased? Is it unbiased? How to calculate expectation of minus logarithm of the sample mean? I don't know. So sometimes it's difficult to find the bias. And let me calculate one more example. Assume that x1, xn have uniform distribution on the interval 0 theta, where theta is positive parameter. So this is uniform distribution on 0 t. This means that the probability density function is just a constant on this interval. And is zero otherwise. You can easily check that this is really density. Integral of 1 over theta is 1. Okay, the first method of calculation of the estimate is method of moments. And if we calculate expectation of x, we get just a point between 0 and theta, so theta over 2. We know that sample mean converges to theta over 2, hence 2 times sample mean converges to theta as n tends to infinity, and it is not difficult to check that this estimate is also unbiased. So unbiased plus consistent. Now let me propose you another method. So we have interval 0 theta. Well, we don't know theta. Theoretically there is theta, but we don't know. And we observe a sample x1, x2, xn. And let me erase this number and let's discuss. So theta cannot be here because all values x1, x2, xn should be belong to this interval. So theta is somewhere here. And now, if n is larger and larger and larger, then you have more and more and more points on this interval. And if you see a lot of points and then nothing here, then probably the maximal point is close to theta. So let's try another statistics. Maximum of x1, x2, xn. And let us check if these statistics, whether the statistics consistent and biased or unbiased. By the way, without calculations, we can say that this statistics is biased. And I have very strong argument. X is always less than theta. So expectation of X cannot be equal theta. So it is biased. However, there is a possibility that we can correct it somehow, maybe multiply by a certain number or just add some non-random variable. Well, but now let's discuss consistency. We want to prove that probability that this maximum converges to theta. So we have to check that this probability minus theta absolute value greater than or equal to epsilon converges to 0 as n tends to infinity for every epsilon greater than 0. So 0 is this, and this is a equation. Oh, well, we know that all x's are less than theta, so maximum is less than theta. So maximum minus theta is greater than 0 if maximum is here. So this point is theta minus epsilon. So maximum is here. Probability that maximum of x1 zone xn is less than theta minus epsilon. Well, maximum is less than theta minus epsilon. What does it mean? All of them are less than theta minus epsilon. Hence, this probability is equal to probability that x1 is less than theta minus epsilon, x2 less than theta minus epsilon, and xn is less than theta minus epsilon. So if maximum is here, then every is less than theta minus epsilon. And if all numbers are less than theta minus epsilon, then maximum. So if and only if. So this is equality. And now x1, x2, xn are independent, identically distributed random variables. So probability of intersection is equal to product of probabilities. Times xn is less than theta minus epsilon. And all of them have uniform distribution. So limit of probability that one random variable is less than theta minus epsilon to the power n. Well, I assume that epsilon is small. So epsilon less than theta. And I have to calculate probability that limit probability that x less than theta minus epsilon to the power n. That x is here, and we have uniform distribution. And the answer is this length divided by theta, or you can integrate the density. So the answer is limit of theta minus epsilon over theta to the power n. And this number is less than 1 to the power n. The limit is 0. So maximum of x1, xn is consistent estimator. And now I would like to correct it. In order to make a correction, I have to calculate the expectation. And to make a correction, I have to find the distribution of maximum. So let's calculate the distribution function. The distribution function of maximum is probability that maximum is less than x, and similar calculations as before, probability that x1 less than or equal to x, x2 less than or equal to x, xn less than or equal to x, and then product of probabilities, and the final answer is x over theta to the power n if x in 0 theta, 1 if x greater than theta, and 0 if x is less than theta, than 0, excuse me, than 0. And if you know the distribution function, you can calculate probability density function, just differentiate with respect to x, and we see that derivative of x to the power n is n x n minus 1 over theta to the power n if x in 0 theta and 0 otherwise. Okay, we know density, so we can integrate. So we integrate from 0 to theta, value x times density, and x to the power n minus 1 over theta to the power n dx is equal to integral of x to the power n, so theta n plus 1 times this n divided by n plus 1, and this theta to the power n is theta times n over n plus 1. If you multiply maximum by n plus 1 over n, then we get unbiased estimator. So corollary, n plus 1 over n times maximum of x1 xn is consistent unbiased estimator of theta. Well, and there is a problem. We have two estimators. For example, this unbiased and consistent, and this unbiased and consistent. And the question is, which one is better? I will answer this question maybe in 30 minutes. But now I would like to discuss the problem. We know how to estimate how to estimate expectation, variance, sometimes parameter. Sometimes we can calculate, we can find biased and unbiased estimators. But how to assume that we don't know the distribution of, so we don't know, is it normal distribution or Poisson distribution or exponential? We know that there is a distribution without any parameter. And the question is it possible to approximate the distribution function, or is it possible to approximate density? And our next topic is the following: estimation of cumulative distribution function and estimation of density. Let me recall you that the distribution function of a random variable x is a probability that this random variable is less than or equal to x small. And let me recall you that probability of the event is equal to expectation of indicator of this event. So we see that the distribution function is expectation of something. So the average of the following random variables converge to the distribution function with probability 1. Moreover, expectation of this mean is equal to fx of x. So this function is unbiased and consistent estimator of the distribution function. Unbiased and consistent. And this function is called empirical distribution function. We will denote it by f hat of x. Sometimes we write index n. So the name is empirical distribution function. Let me make a picture of this empirical distribution function. Okay, let me order this x case and x2, xn. So this is ordered sample. Ordered sample. Sometimes statisticians say that xk is case order statistic. And what is this? This is just minimum of x1, xn, and this is maximum of x1, xn. And please observe that, okay, a little bit later, I'll make picture. Please observe that sum of indicators xk less than or equal to k to x is equal to sum of indicators that the case order statistic is less than or equal to x. Okay, this is xk of x divided by n. Indeed, xk is used here only one times. We know, is it maximum or minimum? And now let me make a picture of empirical distribution function. Let me assume that x has a continuous distribution. Assume that x has continuous distribution. So the function f is continuous. In particular, if you have continuous distribution, then probability that different random variables are equal is equal to 0 if k is not j. So now let me make a picture. So these are order statistics. So this is minimum, this is maximum. And let me recall you that, okay, let me copy this formula. And I would like to make a picture of the function fn of x. So if x is here, then all xk's, or these xk's, are greater than x. So indicators, all indicators are zeros, and the answer is 0. At this point, the first indicator, so on this interval, and at this point, the indicator x1, the first order statistic, is less than x. This indicator is equal to 1. Indeed, x1 is less than or equal to k. But other x2, x3, x4 are greater than x. And the answer is 1 over n. Again, if x is here, then the first order statistic and second order statistic is less than x, and you have the corresponding picture, and so on. And at this point, the answer is 1, and these jumps are equal to 1 over n, 1 over n, 1 over n, and so on and so forth. Okay, so this is a picture. The statement was that empirical distribution function is consistent and unbiased estimator. And the following theorem shows that we have even more general question. We have convergence fn to f of x, not for like pointwise convergence, but even uniform convergence in the whole real line. And this theorem is called Glivenko-Cantelli theorem. Glivenko Cantelli theorem that states that supremum over all x is in R. Empirical distribution function minus true distribution function converges to 0 as n tends to infinity with probability 1. is probability 1. So we have very nice estimator of distribution function. Not only unbiased, but also that uniform, we have uniform convergence, and not for every fixed x. Now let's discuss density estimation. And we assume that let P of x be a density of random variable x, and let k be just a function, be a function with the following properties. It's non-negative. Continuous. However, no, non-negative and such that integral from negative infinity to infinity k of x dx is 1. Sometimes such functions are called kernels. For example, you can take just density, okay, non-negative function integral 1. You can take some density, for example, Gaussian. Or you can take the following function from -1 to 1, 1/2, and zeros here. Or triangular function. The point is 1, 1, -1. And well, let's apply the law of large numbers to the following random variable. K of xk of, excuse me, x minus let me think what is it's better to write x minus xk. Again, by the law of large numbers, these converge to expectation of k x minus random variable x, and we assume that x has continuous distribution and density, so expectation is integral of value, so kx minus y times density p of y dy. Sometimes such integrals are called convolution of functions. So this is a convolution of functions k and p. And now let me introduce the following function k sub h, where h is certain positive parameter, which is equal to k of x over h divided by h. So this function is again a kernel. It's non-negative. Integral is 1. It's not difficult to see. And assume that h is small. So assume that h is small. What happens with the corresponding function? We make this scaling and this, so the function shrinks and expands. So if h become closer and closer to 0, then you will see the following picture. So the functions are smaller, smaller. Okay, it's this peak is higher and higher, and the width is smaller and smaller. But integral is 1. Then, in some sense, this sequence Kn approximates delta function. Kh approximates Dirac delta function, and it approximates in the following sense. So let me write the rigorous statement. So if the function p is continuous, if the density is continuous at point x, is continuous at point x, then integral over r k h x minus y p of y dy converges to p of x as h goes to 0 plus. Well, I will not prove this theorem. However, I want to at least give you a sketch of the proof. Assume that this blue function is y is not y, okay, p of x. What is this function? This function is a peak, is a very peaky function in a neighborhood of this point x. Okay, let me write x0, x0, and this point is x0. And we wish to calculate this integral. And let epsilon be a small number. If x's are here, then the kernel is small. And integral with respect to, if we integrate in this green area, then k becomes smaller and smaller and smaller, and integral here is close to 0. Well, and if y is here, then this function p of y approximately equals p of x0. And if we integrate constant times this kh, then what do we get? We know that integral of kh is 1, and all mass is here, in almost all the mass is here. So the integral from x minus epsilon to x plus epsilon of this number approximately, of this function approximately equals p of x0 times 1. And so you see, this is the statement. Well, this was just a sketch of the proof. However, you can make it rigorous. Select epsilon, very, very small, estimate, integral here, there, and so on and so forth. And now, yes,
sorry,
please.
sorry for the interruption. How about to make a 5-minute break and then continue?
Please give me just 2 minutes to finish, and then we will start the new topic after the break.
Okay, great.
So we know that sum of kh x minus xk over n approximately equals expectation of kh x minus x if n is large and h is fixed. And if h is small, then this expectation approximately equals p of x. So if n is large and h is small, then this so-called kernel estimator of density is close to density. However, you have to be very careful. H should be small, but not so small. If you take H very, very small and n is fixed, then okay, this is a sample. And if H is very, very small, then you will see very picky picture. So 0 almost everywhere and a few very, very high peaks. So there should be some balance between H and N. And now let's make a break and then we will start a new topic.
Okay, thank you very much. And now questions. Do we have some questions in the online audience? Not
No.
okay. Yeah, Anton.
No questions.
5 minutes break, so people here will have to now. Andrey, are you here? Not still not.
Yes.
Yes. So let's continue. Okay, we back.
Okay, and now let us discuss the following question. Which estimates are better? For example, we discussed that sometimes we have different consistent and unbiased estimators of a parameter. For example, maximum or sample mean times 2. And we want to discuss what does it mean better? Better means, okay, closer to unknown parameter. But what does it mean more closer? Because all of these random variables, okay, all of these estimators are random variables. Sometimes with small probability they may be far, sometimes they may be close. And we want to measure distance between estimator and a parameter. And the corresponding topic, the topic is Cramer-Rao bounds. Cramer-Rao bounds. And the general question is the following. We have estimator, we have a true parameter. We want to find difference between true parameter and its estimate and measure it and somehow and make some conclusion. In order to do this, let's introduce so-called loss function. So let W be a loss function. So the loss function is non-negative function such that if so it's a function of two variables. So such that if x and y are close, then this function is small. If x and y are far, then this function is great. And if x is y, then the function is 0. And examples of loss functions are the following: for x minus y squared, or for example, some parameter a times x minus y if x greater than y, b y minus x is if y less than x. And we consider this loss function of this and this and calculate the expectation. And we say that one estimate is better than another estimate if the expected value of losses is smaller. So we say that estimator theta n is better than theta tilde of n if this is smaller. So theta n hat is better in some sense than theta n tilde. Okay, for every theta. Today I will discuss this quadratic loss function, and there are very good theoretical bounds for quadratic losses. So we have theta n hat minus theta squared, and I want to discuss the following question. Okay, can it be small, or how small it can be? Is it possible that for every theta this parameter behaves like 1 over n squared, or some constant over n squared, or some constant over n, or some constant over square root of n? So what is natural to expect at first? And the second question, is there a bound such that you cannot do better? And then if this bound is attained, then you say, oh, this estimator is the best one. Before the formulation of the rigorous result, Kramer-Rao theorem, let me make the following remark. We applied the method of moments, and we calculate. Oh, let me make preliminary calculations. So we know that if we calculate expectation of the sample mean, then we have this. But let's calculate the difference, the expectation of this quadratic risk. I will say that expectation of this is quadratic risk of this estimator. So let's find this. Well, since expectation of sample mean is just expectation of x, then this expression is variance of the sample mean. If you multiply a random variable by a constant, then variance is multiplied by a constant squared. So variance of this random variable is equal to 1 over n squared times variance of sum. And variance of sum of independent random variables is equal to sum of variances. And well, assume that variance is equal to sigma squared. So the answer is n times sigma squared over, n squared here. So sigma squared over n. And if we use some averages, it is natural to expect that quadratic risk behaves as certain constant divided by n. And the aim is to find the smallest possible constant. Well, now assumptions and result. And assumptions. x1, xn is a sample, and we assume that x has a density p of x theta. At first, we consider the case where theta is one-dimensional parameter. Later on, I will discuss the case when theta is multidimensional parameter. And let us assume that this function is differentiable with respect to theta. So regularity conditions. So assume that first, that for every x, the density px theta is continuously differentiable with respect to theta. Differentiable with respect to the parameter theta. And the second assumption is the following. We assume that the set of x's such that px theta is 0, where the density is 0, is independent of theta. Is independent of theta. Well, for example, if density is exponential or normal, then all of these assumptions are satisfied. For example, for exponential density theta e to the minus theta x for positive x and 0 for negative x. Let me denote this. Okay. Then for every fixed x, this function is continuously differentiable with respect to parameter theta. Theta, now this set is 0, infinity. And this set where density is 0 is independent of 0. This set is from negative infinity to 0. Well, another example, normal distribution. Density 1 over square root of 2p sigma squared, exponent minus x minus a squared to sigma squared. Now I consider one-dimensional parameter. So sigma is fixed, a is parameter. Density is not 0 everywhere. So this set is just empty set, and we have continuous differentiability with respect to a. So satisfied, at least for these two densities. Okay, and now assume that t is t of x1, x2, xn. Assume that let t be unbiased estimator of parameter theta. Unbiased estimator of theta. I would like to find bounds for expectation of t of x1 xn minus theta squared. So quadratic risk. Since t is unbiased estimator, this is just variance of t. Okay. Now let's make some preliminary calculations. P is a density, so integral of px theta dx is equal to 1. Now let's differentiate the left-hand side and the right-hand side with respect to theta. So derivative of this integral, let me write, 1 is equal to this. Px theta dx is 0. Okay, now let me make formal calculation and interchange differentiation and integral. Okay, so this is a question. Often you can do this. So this integral is 0. Well, if the density is not so terrible, then it can be proved that you can interchange integral and derivative. So in mathematical textbook, people write P is continuously differentiable with respect plus theta plus P is a nice density such that you can interchange these two integrals. For example, P is dominated from above by some certain integrable function, and the same for derivative. Well, but I don't say such words, but for most of densities, this additional condition is satisfied. Well, and I know that many physicists never think about proving of this and just replace integration and differentiation. Okay, let's continue. I want to say that this is expectation of certain random variable. But to see that this is expectation, I have to write density here, px theta dx. Well, I have density and I don't have p here, so I multiply and divide by p. d over d theta, px theta over px theta. By the way, if this set independent of theta, then if p is 0, then derivative is 0, and okay, there is no, then this formula is true, because sometimes p can be 0. Sometimes p can be 0, but in this case, derivative will also be 0. Okay, and the last step, just notice that this is equal to integral over r derivative of logarithm of the density of x and theta times density dx, and this is expectation of d over d theta logarithm of density x theta. Okay, here x small. And this subindex theta means that true parameter is theta. So let me write this corollary. So expectation of the logarithmic derivative of p x theta is 0. And now let's consider the density of distribution of x1, xn. We assume that they are independent and identically distributed. So multidimensional density is equal to product of densities and is equal to px1 theta times px2 theta times pxn theta. And we make the same calculations. We say that 1 is integral of this product. And we differentiate with respect to theta, and we obtain the following result. Expectation of multidimensional density. So let me write it like x vector valued parameter. So expectation of logarithmic derivative of logarithm of multidimensional density is 0. And now let me continue. So I would like to estimate this quadratic risk. And let me denote this derivative of x theta by lambda of x theta, and I wish to find the expectation of t of x minus okay, let me consider this. Let me at first analyze this. Okay. T is unbiased estimator, so it's theta. On the other hand, this expectation is equal to integral of t of x1 and so on of xn times this multidimensional density dx, and we differentiate left-hand side, right-hand side with respect to theta, and say that 1 is equal to derivative of this, derivative of this, move this derivative here, integral of t of x times derivative of p dx. And we do the same trick as before. We divide by p, multiply by p, and say that this expectation, that this integral is equal to expectation of t of x1, x2, xn of sample times times logarithmic derivative, so this function lambda. Okay, and we have one. So we have one. And this expectation is equal to expectation of t of x times lambda x theta minus theta expectation of lambda. Indeed, expectation of lambda x theta is 0. So this is just notation. So we can subtract theta times expectation and we get the same number. And we continue. And we see the following, that 0 is equal to expectation of this difference of expectation is equal to expectation of difference. We have the joint part lambda and lambda. So t of x, excuse me, 1 is equal to this minus theta times lambda x theta. And we have this beautiful relation. And now let's apply Cauchy inequality. Expectation of product of two random variables is less than or equal square root of expectation of psi squared times expectation of eta squared. So this expectation is less than or equal to expectation of t of x minus theta squared, square root of, times expectation of lambda x theta squared, and square root of this expectation. And what is this? This is quadratic risk of this estimate. So we raise left-hand side and right-hand side to the second power, and we get the Cramer-Rao inequality. Oops. Let's state that this expectation of t of x minus theta squared is greater than or equal to 1 over expectation of lambda squared x theta. So we have certain lower bound, and this lower bound is independent of t. So if t is unbiased estimator of theta, then this quadratic risk cannot be better than this number. And this number is called sometimes Fisher information. So let me introduce notation. E of theta is expectation of lambda squared x theta. So this function is called Fisher information. And this bound is the best. If you have equality, if this expectation squared is equal to 1 over this Fisher information, then we say that that this estimate is effective. Then T is called or efficient estimate of parameter theta. Now let me write you a few formulas for this expectation. Well, and actually it depends on n, because sample depends on x1, x2, xn. So let me recall that this is derivative of logarithm of density, and density is a product. And logarithm of product is sum of logarithm. So this derivative is equal to sum of d over d theta logarithm of the density. Well, sometimes this function is called likelihood function. And observe that these random variables are independent, identically distributed. Moreover, we prove that expectation of this derivative of logarithm of p x theta is 0. So expectation of lambda x theta squared is variance of lambda x theta and is equal to n variances of this, n variances of this variance, yes, of px theta. Well, let's calculate this integral. Oh, by the way, so let me denote this by I small of theta. So this Fisher information is equal to n times certain value that depends only on theta. So Cramer-Rao inequality states that quadratic risk t of x minus theta squared cannot be better than 1 over n I of theta. So the order is some constant divided by n. And now let me calculate, write certain formulas for expectation of logarithmic derivative of p x theta squared. So this variance. Well, certainly you can say that it's integral of derivative of logarithm squared, and derivative of logarithm is derivative of p divided by px theta squared times px theta. So this is a formula you can calculate and integrate. However, there is a simpler formula. And in order to derive a simpler formula, let's calculate the second derivative of logarithm. So derivative of this so second derivative of numerator of p times p x theta minus numerator times derivative of denominator px theta squared over p squared x theta. And now let me calculate expectation of the left-hand side. The expectation of the second derivative of logarithm of p x theta. So this is just nice guess. Is equal to integral of this derivative d2 over d theta squared of logarithm p x theta times density dx is equal to, okay, we have a formula, we write integral second derivative times p over p squared times p, so second derivative of the density dx minus, minus what? Derivative squared divided by p squared. So minus integral, and derivative divided by p is logarithmic derivative. D over d theta log p x theta squared times excuse me, okay, something yes, and times, yeah, I forgot about this density, times px theta dx. And now the first integral. So let's interchange integral and derivative. Okay, as usually you can do this. And integral of p is 1. So the second derivative of 1 is 0. And what is this? And this is minus expectation of d over d theta logarithm p x theta squared. So sometimes you can calculate Fisher information using this formula, and sometimes you can calculate Fisher information using this formula. So important corollary is expectation of lambda en of theta is equal to x theta squared is equal to minus expectation of d over d theta of lambda x theta, and is equal to minus n expectation of d2 over d theta squared logarithm of p x theta. This is one-dimensional random variable. Sometimes it's easier to apply this formula if you wish to calculate Fisher information. Sometimes this formula, n expectation of d over d theta logarithm of p x theta squared. And few remarks about multi-dimensional case and about generalization of Cramer-Rao inequality. One generalization is the following. Assume that T is not unbiased estimate of parameter theta, and assume that expectation of T of x is certain function g of theta, which is continuously differentiable, and assume that the density is nice and satisfies regularity conditions. Then T of x is unbiased estimate of parameter g of theta, and it can be proved that variance of T of x, which is equal to expectation of T of x minus g of theta squared, is greater than or equal to g prime of theta squared, so this is derivative, over Fisher information. And observe that the right-hand side is independent of t. So the best value for quadratic risk, if you estimate g of theta, is this. Well, and now consider multi-dimensional case. Multi-dimensional Cramer-Rao inequality. So we assume that x1, xn are random variables or random vectors with density px theta, where theta is multi-dimensional parameter. Theta is theta 1, theta p, multi-dimensional parameter. We assume that p satisfies regularity condition. Assume that px theta satisfies regularity so p is differentiable with respect to theta. So p is non-zero in a certain set, which is independent of theta, and that you can interchange derivative and the integral. Then you do the same calculation as we did in one-dimensional case, apply Cauchy inequality, and the following theorem can be proved. But I need to introduce the following notation. Let me denote by IMK of theta the expectation of the product d over dm logarithm of px theta d over d theta k logarithm of px theta. So this is multidimensional density, and introduce the matrix E of theta is matrix of all these expectations. EMK of theta, M and K from 1 to P. E of theta is called Fisher information matrix. And it can be easily seen that this expression is equal to n times expectation of partial derivatives of logarithm of px. So this is vector, this is just one random variable, px theta, derivative of log of p, x theta. And result. Assume that t of x is unbiased estimate of multi-dimensional parameter theta. And assume that density satisfies the regularity conditions. Then covariance matrix of this estimate is greater than or equal to inverse matrix, inverse of Fisher information matrix. Okay, I forgot to say what does it mean that matrix is greater than matrix. This means that A is greater than or equal to B. I mean the following, that A minus B is positive definite. This quadratic matrix is non-negative definite, non-negative semi-definite. Or this inequality is equivalent to the following. For every vector V in Rp, variance of T of x times V, so this is scalar product. So this is one-dimensional random variable is greater than or equal to vector V transposed times inverse of Fisher information matrix times V. And this variance is equal to expectation of difference T of x v or T of x minus theta times v, this is scalar product, squared. So this is a quadratic risk of estimate Tx times v of parameter theta times v. So we have lower bounds for risk. Maybe the final remark, I have just 1 minute, that if expectation of T of x is a function psi of theta, which is continuously differentiable, then covariance matrix of T of x is greater than or equal to the following matrix. Well, let me denote derivative of psi by phi. So this is matrix. This is matrix of partial derivatives. And we have the inequality phi of theta times inverse of Fisher information matrix times phi of theta transposed. In one-dimensional case, this is just a derivative, and we have g prime or phi prime, psi prime squared divided by Fisher information. That's all for today. Thank you for your attention.
Thank you very much. Let's thank our speaker. And now, questions? Andrey, maybe I have a question, because for tomorrow we also need some method which is called maximum likelihood estimation. Can you sketch it very quickly?
Yes, sure. Thanks. I can. Yes. Today we discussed only methods of moments, law of large numbers, and their applications. However, there is one very good idea how we can calculate an estimator, and this way is quite smart. Moreover, usually, no, not usually, but for almost all cases, you can even imagine this method gives you consistent estimator. And this method is called a maximum likelihood estimator. Maximum likelihood estimator. I will write MLE. And idea is very simple. We start with example. Assume that you have a coin. Well, assume that you have 2 coins. One coin is the following. Heads with probability 99% and tails with probability 1%. And another coin is this. Heads with probability this and tails with probability 99%. And you toss a coin 3 times and you see heads, heads, heads. It may be the first coin or it may be the second coin. But if you ask yourself what is more likely, the answer is certainly coin number 1, because probability that you have 3 heads in a row is 99 cubed.
Yeah, okay.
And for this coin, you have heads, heads, heads with probability 1% cubed, which is much smaller. And now let's start with experiment. Assume that you have a sample x1, x2, xn with a density p x theta. Then what is the density, or with a probability p x theta probability that random variable have this value. What is the density of this sample? At the point x1, x2, xn, a product px1 of theta times px2 of theta times pxn of theta. And maximum likely... Pardon?
Andrey, please wait.
I'm sorry, I don't hear.
Yes.
Yeah, I also can't hear you.
Do you hear me now?
No, I hear you. I cannot hear Andrey Semenov.
Andrey, could you please repeat your question?
Oh, I think they just I think the internet, something happened to the internet connection. Yeah, okay, I think it's they have some internet problems on their side.
But now it works.
Well, okay.
Okay. Now we hear you. And now we want to maximize this density and find maximum in theta. And now parameters x1 and xn are fixed. And we say that estimate theta star is the maximum likelihood estimator of parameter theta if p of x1 theta star, p2 theta star, px and theta star is equal to maximum over all thetas of this product. So you just maximize the density or the probability that x1 is equal to this number, xn is equal to this number. Sometimes you say that theta star is argmax of this expression. And now you can ask a question, and how to find the point of maximum? And the answer is simple. Just recall mathematical analysis. You have to differentiate with respect to theta and solve equation. Derivative is 0. However, I don't like to maximize to differentiate the product. And notice that theta is a point of maximum of product if and only of this function if and only if theta is maximum of logarithm of the product, logarithm of this. And logarithm of a product is equal to sum of logarithms of theta of sum of logarithms of xk of p xk theta. By the way, today we saw this expression when we discussed Cramer-Rao inequality. Okay, and how to find maximum. Let's consider this function, differentiate with respect to theta, and solve the equation. Derivative of this sum logarithm of p xk theta is 0. So sum of k from 1 to n logarithmic derivative of this is 0. Sometimes this equation is called likelihood equation. And you solve this equation, maybe numerically, and then you find the point of maximum, or assume that you have few subspecies for points. You have to select where the maximum is attained, and after solving this equation, you can find maximum likelihood estimator. Well, few remarks. It's easier to study sums than products, and to maximize sums or than products. The second remark, sometimes you can solve this equation explicitly. For example, for normal distribution, for Poisson distribution, for exponential distribution. If the density is Cauchy density, there are a lot of numerical algorithms how to solve sum of certain functions is zero. And in many cases, maximum likelihood estimator is effective in the sense of Cramer-Rao inequality. Well, very often, not always, but very, very often. And the idea is nice. And the last remark, as I told you, if the density is not too terrible, for example, if it is continuous in theta, and if theta belongs to a compact interval, then the maximum likelihood estimator gives you consistent estimate. So this is a rigorous result. So it can be proved. The proof is not obvious. It is complicated, that under very mild assumptions on the density, maximum likelihood estimator gives you consistent estimator. Okay, thanks.
Thank you. Consistent but biased can be.
Yes, consistent but biased.
Can be biased. Okay, thank you very much, Andrey. Thank you very much.
Yes, thank you very much for your lecture.
Yes, some questions about fission information. Tomorrow you will have at the morning lecture by Professor Gerardo Adessa, and fission information, Cramer-Rao inequality. This is exactly what we need for quantum metrology. And this will be, and all these things about super resolution imaging, how to see coin from the space, and all these things, this will be exactly based on this inequality. So my recommendation for you, my advice for you is just to look again at this lecture today if something is unclear for you, because tomorrow this will be even more interesting. Yeah. Yeah, please.
The question is if we will have the recording. Can you get the recording after the... Yeah, okay.
I don't know if we can, but I believe we will do it. We will try. Okay, other questions? Anton, do we have online questions?
No, we don't.
No. Okay, then let's thank our speaker again. And
Okay.
the job. So online, see you tomorrow. Tomorrow morning we have very nice lecture also. And let's see what happens.